Welcome to the Sky Commander Flight Brief. It's your mission-ready podcast for drone pilot training and aerial insights across Canada.
From Transport Canada rules to real-world drone ops, we break it down, take you higher, and help you earn your wings. Because here at skycommander.ca, we don't just fly.
It hints there's more to it. It's a masterclass, a deeper level, maybe a philosophy or a community focus, perhaps.
It's definitely intriguing, sets them apart from just, a basic tips show. Skycommander.ca is the obvious next step. Precisely. If you're thinking about flying a drone in Canada, boom, this content is aimed right at you.
Powered by skycommander.ca.
The elite podcast for Canada's drone pilot. Okay, let's get started. Today we are taking on, what is probably the biggest hurdle for scaling unmanned aviation on a global scale. How do you prove safety when the aircraft is miles away and all the risk is happening completely below your sightline?
Right.
We are diving deep into beyond visual line of sight BVLOS ground risk, and we're using the very detailed systematic framework that the FAA proposed in the August 7, 2025 Notice of Proposed Rulemaking for Part 108.
And that framework is really the critical piece of the puzzle here. I mean, if you're operating drones today, you're probably working under a Part 107 waiver.
Yeah, most likely.
And that's what we call the artisan era of UAS.
Yeah.
Every single flight is this bespoke project you have to negotiate, case by case with the FAA.
Right. It's a one-off.
It's a one-off. For BVLOS to move from that artisan work to a truly industrial, scalable, utility-think deliveries, infrastructure inspection, large-scale mapping, that case-by-case stuff has to stop. We need a reliable, repeatable national standard for managing ground risk.
Okay, so let's break this down. Our mission here is to get you, the learner, past just the high-level summary. We want to give you the precise philosophy, the robust workflow, and frankly, the language you need to start operating with a Part 108 ready mindset, specifically when it comes to public safety. Because when we talk about safety in this context, we are really talking about ground risk.
Yeah, and that's the anchor. Ground risk is, the risk of harm to people and property from a UAS failure or any kind of off-nominal event. And Part 108 is all about forcing operators to treat that risk systematically.
Systematically how?
It leans on this fundamental safety concept that risk is a calculation. It's the probability of something going wrong multiplied by the consequence if it does.
Okay.
With BVLOS, that probability part gets harder to completely pin down. You're trusting systems over your own eyeballs. So the Part 108 model demands that we ruthlessly control, measure, and mitigate the consequence side of that equation.
And to structure that consequence, the sources all point to three primary hazards on the ground. We've been calling it the PRB framework.
PRB, people, roads, and buildings. Those are your non-negotiable consequence drivers.
And this framework is what allows for that huge shift in mindset, right?
Yeah.
From the see and steer of visual line of sight.
Exactly, VLOS.
To this really rigorous plan and prove model that you need for industrial scale. The FAA is trying to make the answer to ground risk measurable, repeatable, and just baked into routine planning. It's not about a pilot's gut feeling anymore.
It's a tectonic shift for the industry. It really is.
So let's start with that foundation of standardization. It seems to all begin with population density. You said we need consistency across the entire national airspace system, the NAHLs.
We have to. I mean, imagine if every operator used a different map or had their own definition of what urban means. The whole system would be completely unmanageable for regulators.
A total mess.
Total mess. That lack of standardization has been the main bottleneck holding BVLOS back. The scale we're talking about, it demands that when operator A flies over a suburban park and calls it a medium risk zone, operator B, flying the exact same mission, has to arrive at the exact same conclusion using the exact same metrics.
So Part 108 is trying to force that consistency.
It is. It's moving us away from subjective hazard assessment and toward quantitative risk management.
And the main tool for that seems to be these 5 specific categories of ground risk, all based on population density.
Correct. And these categories, they basically establish the duty of care that's required. More people under the flight path means a higher potential consequence of failure.
Which in turn means you need more discipline, more mitigations.
Precisely. That's why we say density drives duty.
Okay, let's break those categories down because the difference between the first few feels really important for a learner to get. What defines a true low-risk Category 1 operation?
So Category 1 is your baseline. It's for operations with just minimal public exposure. The proposed rule defines it as operating farther than 1 statute mile from any Landscan cell that has 10 or more people in it.
So really remote.
Really remote. Think large-scale pipeline inspections across hundreds of miles of empty desert, or surveying vast farmlands nowhere near a town. If you fail out there, the chances of hitting a person are, mathematically negligible.
Okay, so that's the goal if you want the least friction. What happens when we step up to Category 2?
Category 2 is where most utility and sort of corridor operations will probably live. You're still in low-density territory,
Yeah.
but now you're operating within 1 statute mile of a land scan cell that has 10 or more people.
So you're getting closer.
You're getting closer. Imagine that same pipeline, but now it crosses a remote access road, or it passes near a little cluster of mobile homes. The risk profile shifts instantly. You go from being completely clear of people to acknowledging a latent human presence. And that small shift requires a huge leap in your planning rigor.
And then, of course, you've got Categories 3, 4, and 5, which ramp up the density quite a bit.
They do. Categories 3 through 5, that's your transition into urban, semi-urban, and eventually dense metropolitan airspace. This is where the consequences get very high, and managing the probability gets really tricky.
Why?
Well, you're dealing with electromagnetic noise, degraded GNSS signals, complex air traffic. So the categories are set up so that once you hit Category 3, your operation triggers these explicit regulatory requirements, specifically something called strategic deconfliction services.
So you can't just rely on your own plan anymore. You have to coordinate.
Exactly. You need network coordination because the probability of some kind of conflict is just too high to manage alone.
And all of this hinges on having one standard for what population means. That brings us to the data set. Landscan USA.
Landscan USA, developed by Oak Ridge National Laboratory. And its selection was very strategic. First, it's free and publicly available, which lowers the barrier for small operators.
That's a big deal.
It is. Second, it's machine readable, which means you can plug it right into your flight planning software for automated risk assessment. And third, it gives you high-resolution population estimates down to these tiny 90-meter grid cells.
But the really crucial detail, the one that makes this so complex, is that Landscan isn't just one static map. It has separate day versus night data.
Yeah, the day-night different flight principle is absolutely foundational to Part 108. Population isn't static, it flows. A commercial district might have a density score that puts it squarely in Category 4 during business hours.
Right, everyone's at work.
But after 6 p.m., that same geographic cell might drop all the way down to Category 2. And conversely, a quiet suburban neighborhood might spike in consequence in the afternoon, when school lets out.
I see the need, but I have to push back a little on this for the average learner. Using dynamic time-of-day data feels like a huge operational burden. Is it really feasible for a small BVLOS company to build that into every single flight plan?
And that is precisely the transition. Part 108 is mandating. The technology has to follow the safety requirement. We're moving away from someone manually checking a map.
Okay.
Part 108 readiness means you integrate those data sets into automated mission planning tools. The operator doesn't check the grid cell. The system does. You just tell it your planned takeoff time, and the system automatically pulls the right Landscan layer. And it has to use the most conservative estimate for your flight window. If you can't automate that, you aren't really Part 108 ready.
Okay, so people risk is the baseline, managed by those Landscan categories. Let's move to the second part of PRB roads risk. Why do roads need their own special attention? Aren't the people on the roads covered by Landscan?
They are, technically, but that misses the specific catastrophic consequence that roads introduce. Roads are special because the harm is often exponential and indirect. We call it the secondary accident.
A secondary accident.
Think about it. A driver's going 65 miles per hour down a highway. Even a small, non-lethal drone hitting the windshield, or even just a near miss, can cause them to panic, slam on the brakes, swerve.
And that single incident then cascades?
Exactly.
Okay.
You've just traded a low-energy drone impact for a high-speed, multi-vehicle pileup involving dozens of people. The magnitude of that consequence is just so much larger than if the drone hit an empty field.
So for professional BVLOS planning, we need more than just population data. We need detailed road layers.
Absolutely. You have to analyze road classification. Is this a little local road where speeds are 25 miles an hour? Or is it a major interstate where vehicle density and speed are maxed out? You have to treat high-speed roads as explicit consequence hot zones.
What about the geometry of the road? I imagine where you cross it matters, too.
It matters a lot. Think about crossing a highway just as it enters a tight S-curve, or near a big interchange, or on a bridge. In those spots, a driver's margin for error is basically zero. A crash in a tunnel or on a bridge is exponentially riskier because traffic is compressed and emergency response is, seriously hampered. This forces operators to either reroute entirely or mandate very specific mitigations, like flying higher or having a parachute armed, just for those precise segments.
Okay, that brings us to buildings, the third piece of PRB. And I think this is where the biggest misconception is, especially for operators who are used to VLOS logic. The assumption is flying over a building is a good thing. It provides a shelter factor.
That assumption is dangerous, and it's one we have to challenge. The source material is crystal clear on this. The FAA explicitly considered, analyzed, and then rejected the idea of granting a shelter factor credit for flying over buildings.
Why? I mean, if the building is solid, why not credit the protection?
Two main reasons. First is a data challenge. Like we said, Landscan knows how many people are in a grid cell, but it has no idea if they're inside or outside on the first floor or on a rooftop garden. So you can't reliably model it.
You'd be making an assumption that data doesn't support.
Exactly. And second, and maybe more importantly, is the kinetic energy problem. A tiny drone might be stopped by a roof, sure, but the FAA is planning for an industrial scale. We're talking about heavier, more complex aircraft. A big, heavy drone could still cause structural damage, penetrate the roof, or even start a fire.
So for consistency, they just said no.
Right. To be safe across the whole range of BVLOS aircraft, up to 1,320 pounds, the FAA's position is, do not plan as if rooftops magically reduce your compliance burden. You have to assume the risk is still there.
That's a huge insight. Don't rely on architecture for regulatory relief. But some buildings are still more important than others, right? Even if there are no people around.
That's the other side of it. Even in a zero population area, some structures are what we call critical consequence targets. They have to be avoided. We're talking about critical infrastructure. The consequence of hitting a high voltage substation isn't measured in human lives, but in economic disruption, power outages for thousands of people.
What else is on that list? What are the non-negotiable avoidance targets?
Refineries, fuel terminals, natural gas pipelines, hospitals, major telecom hubs. Basically, any site where an impact results in an immediate and massive systemic failure. Your assessment has to include not just building footprints, but an updated layer of that critical infrastructure with specific no-fly zones around them.
So that PRB framework sets the boundaries. Now we have to talk about the workflow because Part 108 is all about a rigorous, repeatable process.
Right. This is the instruction manual for that plan and prove mindset. It turns all that theory into actual, actionable steps. The full checklist is map, classify, segment, soar, mitigate, prove, apply, debrief.
But before we even get to the map, there's a step 0. You call it the ConOps snap.
The concept of operation snapshot. It's essential because your ground risk is totally linked to the specific technology and purpose of your flight. You have to anchor 5 things: mission purpose, the aircraft and payload, your route specs like altitude and speed, the C2 or command and control method, and finally, your operating basis. Are you a Part 107 waiver or aiming for a Part 108 certificate?
Why is the C2 method so important for ground risk? That feels more like an air risk thing.
It's a huge ground risk driver. Your C2 integrity directly affects the likelihood side of the risk equation. If you're flying a fast fixed-wing drone with a single weak cell link in an area known for bad signal,
your probability of it falling out of the sky goes way up.
Way up. The probability of an uncontrolled descent or a flyaway just skyrockets. The ConOps snap forces you to admit that weakness before you even plot a single waypoint over a populated area.
Okay, so once we're anchored, we start the assessment. And the first big step is segmenting the route. Why isn't it good enough to just average the risk over a 10-mile flight?
Averaging is the enemy of good mitigation. It hides the danger. If you have a 10-mile route that's super safe, Category 1 for 9.8 miles, but it crosses a crazy busy Category 4 highway interchange for just 200 meters.
Averaging that out makes it look totally safe.
Totally safe. But that 200-meter segment is still a catastrophic hotspot. If you don't break the route into small, manageable chunks, say 100 to 500 meters, you'll never identify the specific zones that need targeted engineering controls.
So segmenting gives you precision. Each little segment gets its own PRB score, and you end up with a risk heat map of your route.
Precisely. And that lets you tailor your mitigations. Maybe segment 42, the highway crossing, requires a parachute to be armed and ready, while segment 43 over an empty field just needs standard battery margins. That precision is the difference between a compliant Part 108 plan and a vague waiver application.
Now we have to define the area we're actually assessing. The drone doesn't just threaten the single point right below it. We need to define the failure footprint.
This is arguably the most essential piece of engineering in all of this. The failure footprint is the total ground area the aircraft could hit if a failure happens at a specific point. And it's way, way wider than just the flight path itself.
Okay.
Its size is driven by altitude, the aircraft's speed, and the wind.
Can you give us an analogy to help get our heads around the scale of this?
Sure. Imagine you're flying at 400 feet. If your aircraft loses all power, it's not going to fall straight down. It has forward momentum and the wind will push it. If it's a fixed-wing UAS with, say, an 8-to-1 glide ratio, from 400 feet it could glide 3,200 feet laterally. That's almost a kilometer.
Wow. So altitude is a massive multiplier. The higher you fly, the wider your safety buffer has to be.
Correct. The operator has to define a conservative lateral buffer around the route and treat that whole wide band as the true impact zone. This means if your buffer is 300 meters, you have to make sure there are no high-consequence PRB hotspots within 300 meters on either side of your flight path. It's a serious engineering task.
Okay, so we have segments, we have a defined footprint, now we get to the math. Scoring likelihood times consequence. How do we figure out those scores?
The scoring is usually done on a simple matrix, like a 3x3 or a 5x5, to get a relative value. The key is knowing what drives each side of that equation.
Let's start with the likelihood drivers, the things that increase the probability of a failure.
Likelihood is all about your system's integrity. So, number one is the aircraft reliability history. Does this model have a good track record? Number two, battery health and margins. Are you pushing your batteries to the limit? Number three, C2 quality. Do you have redundant links? 4, the GNSS environment. Are you flying in an urban canyon with bad signal? And 5, automation maturity. How good is your geofence?
And on the other side, the consequence drivers are just our PRB framework again.
Absolutely. Consequence is driven by the land scan population density category for that segment,
Yeah.
the road class and time of day traffic is at rush hour on an interstate, and the presence of any building criticality. Are you flying over a hospital?
And the whole point of the scoring exercise is to find the hotspots.
The hotspots are the segments where that final risk score is just unacceptable and you must mitigate it. The power of this system is that it finds nodes that might look fine on a simple map. A patch of empty land could become a hotspot if its GNSS signal is band high likelihood and it's right next to a water treatment plant high consequence. Identifying those hotspots tells you exactly where to focus your energy.
Which leads us right into the mitigation hierarchy. This is where the professional operator really shows their stuff. You don't just find risk, you engineer it out. The hierarchy is avoid, prevent, soften, respond, prove.
And the key insight here is that not all mitigation is created equal. You have to prioritize the levers that give you the biggest reduction in systemic risk.
And number one on that list is always avoid exposure. The best ROI.
It's the best ROI because it's the easiest and cheapest way to reduce consequence. If you can just shift your flight path 50 meters to the left to avoid a Category 2 pocket and stay over a Category 1 zone instead, you just engineered out an entire layer of risk and regulatory duty.
Give me some specific examples of avoidance.
For people avoidance, it's about micro-routing. Instead of flying straight, use a small lateral offset to hug the side of the corridor with the lowest population density, or you time shift. Flying near a school, don't fly at 3 p.m. during pickup, fly at 10 a.m.
Okay.
For road avoidance, you cross highways at their narrowest point to minimize your time over the hazard. And if you can, you fly next to the road over open land, not directly over the high-speed traffic. For buildings, you use strict no-fly polygons around those critical sites.
So once you've avoided everything you can, you move to step 2, prevent failure, reducing the probability.
This is all about system reliability and discipline. Part 108 demands robust procedures. That means strict, documented maintenance cycles, automated pre-flight health checks, redundant C2 links, all of it.
You also mentioned that for the really dense areas, categories 3 through 5, Part 108 emphasizes strategic deconfliction. How does that reduce ground risk?
It's indirect, but it's fundamental. Strategic deconfliction, using services often called USS or UAS service suppliers, coordinates all the aircraft in that dense airspace. By making the airspace predictable and coordinated, you drastically reduce the chance of a mid-air collision.
Which is a type of failure that often leads to an uncontrolled descent.
Which leads to an unplanned ground impact in a populated area. Exactly.
So step 3, soften consequences. If avoidance and prevention don't work, how do we limit the damage?
This is about physical controls. The most common one is a ballistic recovery parachute. If you have a parachute, your failure footprint calculation changes completely. The impact point becomes more predictable and the terminal velocity is much lower, so you can sometimes fly over slightly higher consequence zones.
And the FAA even ties aircraft design to this, right, with weight limits and things.
They do. The NPRM mentions things like a proposed 25-foot lateral span cap and a max gross weight of 1,320 pounds for certain aircraft. The FAA is making a trade-off. We'll let you fly bigger drones for BVLOS, but only if you limit the size and mass enough to keep the kinetic energy manageable if something goes wrong.
Step 4. Response planning. This is the emergency script, and you call it lost link ethics.
This is what separates the pros from the amateurs. Lost link ethics means your automated fail-safe behavior return to home, loiter, land, has to be explicitly evaluated for its PRB risk. You can't just trust the factory default setting.
The rule has to be that the aircraft, if it gets lost, is programmed to go somewhere safer than the primary route.
Exactly. This means predefining contingency routes and alternate landing zones that you know are in low-risk Category 1 areas. You have to make sure your return-to-home path doesn't accidentally send a lost drone straight back over that highway crossing you tried so hard to avoid.
And finally, the last step, the capstone. Prove of the safety case. You call this building a Part 108 ready habit.
This is the entire point. The FAA is moving from judging intentions to assessing evidence. The plan and prove leap means your mission package isn't just a flight plan, it's a full-blown regulatory safety argument.
Then what does that evidence actually look like for the learner?
It's structured data. It's map overlays showing your failure footprint and the land scan layers. It's a segment-by-segment risk table with your likelihood and consequence scores. It's a written rationale for your route choice. We chose Route B because it reduced time over Category 3 zone by 45 seconds, and it's documentation of your contingency logic.
I have to challenge this again, though. This sounds incredibly rigorous, almost prohibitively so, for a small operator just trying to run a simple patrol flight. Is this burden of proof going to stifle growth?
I mean, it creates a barrier to entry, no doubt, but it also creates professionalism. The FAA is saying that if you want to operate scalable BVLOS, you have to treat it with the same engineering rigor as manned aviation. The cost of compliance gets spread out over hundreds of routine flights.
So you build a safety case once and then reuse the framework.
Exactly. And the leading operators are already doing this because it turns them into a data-backed safety voice. They can go to the FAA and say, we've flown 1,000 hours, and our route architecture has reduced high-density overflight by 65%. That kind of data builds credibility that money just can't buy.
So we've spent all this time talking about Layer A, the static map, the pre-planned route, but the real world is messy. What happens when the map is just plain wrong? When dynamic reality, or Layer B, takes over?
Ground reality is always in a state of drift. The world doesn't stand still for your flight plan. People risk changes, a protest pops up, roads risk changes, a traffic jam, even building risk can change. A construction crane suddenly appears on a rooftop.
So the professional operator has to stack that static Part 108 logic, Layer A, with a dynamic reality layer, Layer B.
Layer B is your real-time intel. Live traffic feeds, weather alerts, incident command advisories. The system has to be designed so that Layer B can interrupt, redirect, or even abort the mission if there's a sudden PRB spike on the ground.
Which requires a repeatable decision-making process, not just pilot heroics.
No heroics. We need an algorithm. The one we use is simple. Detect, classify, choose, execute. It forces a calm, measured response.
Okay, let's run a scenario through that. A drone is 15 minutes into a long inspection flight.
Okay. Your ops intel feed pings you. You detect a large, unauthorized pop-up gathering, a small festival right next to segment 75, which you had scored as a safe Category 2.
Okay, so step 2 is classify.
You classify that change as a sudden people spike. It's pushed the local density up to Category 4. It's now an unacceptable hotspot.
Step 3, choose.
You choose your pre-planned response. You have 2 alternates ready to go. You select alternate A, which routes you on a 500-meter lateral offset around the whole festival area over some empty land.
And finally, execute.
You execute the route change command. You verify your C2 link is solid. And maybe you even slow the aircraft down a bit near the congested area just to be safe. It's methodical. It's non-heroic. And that is what Part 108 resilience is all about.
To even enable that kind of mid-flight change, the planning has to include what you call a surprise-ready flight pattern.
This is the blueprint for resilience. A primary route is not enough. You need a primary route plus 2 alternates plus hold points plus an escape corridor. The hold points are safe. Category 1 zones placed just before and after any high-risk segment.
And to make that actionable, you need hard gates and triggers.
Absolutely. You define strict entry criteria for every risky segment. For example, the gate to enter a Category 3 segment might be battery must be above 65%, C2 link must be 98%, and wind must be below 15 knots. If any of those fail, the rule is unambiguous. Hold or reroute, not continue and hope.
And it's important to note, this isn't just an FAA thing. This structure gives you a kind of global credibility.
That's right, it gives you global fluency. This whole PRB density-based approach aligns almost perfectly with international frameworks like the Gerasora methodology used all over Europe. If you can demonstrate Part 108 readiness, you have immediate cross-border credibility.
And we keep coming back to this idea of becoming a data-backed safety voice.
Because that's the currency of this new era. You use your documentation, the risk tables, the incident logs to collect safety metrics. You prove you're getting safer. You show regulators and clients that you are systematically reducing your ground exposure.
Okay, to wrap this all up, let's do some rapid-fire myth busting on the 3 key ground risk myths that Part 108 just demolishes.
Let's do it. Myth 1, buildings equal safer.
Fact. The FAA rejected the shelter factor. They can't model who's inside, and heavy drones are still a risk. Do not rely on rooftops.
Myth 2, rural equals trivial risk.
Fact. Nope. High-speed roads and critical infrastructure can turn a rural segment into a catastrophic hotspot. Consequence is not just about population.
Myth 3, the shortest route is best.
Fact. Under Part 108, the safest route is the one with the fewest high-risk segments, even if it's longer. You prioritize avoiding consequence over efficiency. Okay, let's apply all that to a quick scenario. A power line inspection that has to skirt a small hamlet. It's a low-density pocket, but it spikes the segment from Category 1 to Category 2.
Okay, assessment first. It's Category 2 for people, it crosses a local road, and there are residential buildings. That's an unacceptable hotspot.
So we need mitigation.
We start with avoidance. Use a 25-meter lateral offset to shift the route away from the houses. We time shift the flight to mid-morning to avoid people being outside. Then, maybe soften. Make sure a controlled descent system is active for that specific segment.
And critically, the lost link ethics.
The lost link plan has to direct the aircraft away from the hamlet if it fails. The return-to-home path has to exit toward the empty farmland, not fly back over the center of town. That's the plan-and-prove mindset baked into every single layer of the operation.
Okay, so let's try to bring all these layers together for you, the learner.
The big takeaway is that ground risk in scalable BVLOS isn't something you react to. It is something you must engineer into the route, the contingencies, and all of your assumptions before you even think about launching.
Right. And density drives your duty. That's why the FAA is proposing those 5 standardized categories using the Landscan dataset with both day and night layers.
And your core analysis has to focus on people, roads, and buildings. And please remember, the building shelter factor was explicitly rejected.
The roadmap to get ready for Part 108 requires that systematic, evidence-based workflow map: classify, segment, score, mitigate, prove. And that mitigation hierarchy always starts with avoidance. The best ROI is just not being over the hazard in the first place.
And what really separates the professionals is resilience. It's building a safety case that stacks that static Landscan map with a dynamic reality layer and ensuring your emergency protocols, your lost link ethics, always direct the aircraft towards safety.
And that brings us to the final provocative thought for you to really chew on, building on that idea of dynamic reality. If the FAA is mandating this move away from an artisan subjective system to an industrial one based on structured, repeatable evidence, what system or data layer that you're currently using outside of the official NPRM might be based on a stale assumption? We're talking about assumptions. Are you assuming your map data is granular enough for a specific neighborhood? Or do you need to challenge that with some visual recon? Are you assuming 6 a.m. traffic is always light? Maybe you need to formally register and challenge that assumption before your next flight over a commuter route.
You have to challenge your assumptions.
Go back and look at your current flight plans through this rigorous, evidence-based lens. Challenge your assumptions and become a data-backed safety voice.
That's the goal.
That's a wrap on today's mission, Commander. See above, go beyond, get ahead. For more training, tools, and intel, head to skycommander.ca. If you learned something new, share it, subscribe, and leave us a 5-star debrief.